Hello. So today we are going to talk about multiplexed and demultiplexed signals. Um, this is a lesson where this year, with all the pandemic and everything, we're not really going to have access to multiplexers and demultiplexers because they don't have it in the Multisim Live accounts that we have, and they don't have it in Tinkercad. So we're just going to talk about it and learn about it a little bit. And so as long as we just understand the basics about what a multiplexer and demultiplexer, what they are, then that's pretty much all we're shooting for with this lesson. So we want to understand what multiplexing and demultiplexing is, and it sounds a lot more intense than it is. And we'll talk about a little bit of the logic circuits. We'll go through a little bit to see how they work. So, oopsie. Okay, so this is a lot. You don't have to write all this. This is just telling us what's going to be in this lesson. We're going to talk about the basic function of multiplexers. So this is kind of we're gonna go into that. The applications of a multiplex. We'll talk a little bit about the 4-to-1 and the different scales, and then we're gonna. So the things I'm checking here are the things that you want to focus on during the lesson. And those are going to be the things that I'll tell you, hey, this is the stuff that needs to go in your notes. So basically these topics here, what does a multiplexer do? And then how do we use them? What does a demultiplexer do? How do we use it? And then see how those interact with our 7-segment displays and how we would use them. So multiplexer, MUX, is how you shorten it to write. Basically it's a digital switch that has multiple inputs or sources and a single destination. So it's kind of like a switch that you need to select which it selects which input to send to the output. There are inputs, there are select lines. The inputs, we'll talk about what those will be, but the select lines, those are basically going to be switches that count in binary. 0, 0, if you have 2 select lines, then you would get 4 possible combinations, right? In binary, 0, 0, 0, 1, 1, 0, and 1, 1. So if you have 2 select lines, just those are switches, and that means that you're going to have 2 to the n inputs. So if you have 2 select lines, 4 inputs. If you have 3 select lines, that'll be 8 inputs. 4 select lines would give you 16 inputs. My screen is gray. Is it showing up gray for everyone online? Ooh. Maybe Alejandro, maybe try like exiting out and then joining back in. See if that helps. I know I sound like your basic IT guy. Just try unplug it and plug it back in. See if that works. So the next slide is going to show us a kind of a visual representation of what a multiplexer does, and I think it will be more helpful than all this text. But I'll wait a second because I know some people are still trying to write this down. Oh, I'm glad, Alejandro. Good. Glad that worked out. Okay, so let's take a look at an application of what a multiplexer might be used for. So here's an application where we have multiple sources, and one of them needs to be selected in order to be the output. So in this case, our output is our single destination, would be our surround sound speakers. And we have, in this situation, we have 4 different inputs. And then what would happen is these little switches over here, B and A, would be, you would just set them. There's 4 different configurations. And so 0, 0 would let this signal through. 0, 1 would let this signal through. 1, 0 would let the D2 signal through, and 1, 1 would let the D3 signal through. So, and it's just based off the configuration of these 2 selector lines or switches. And so, so this kind of gives you an idea of what sort of a situation a multiplexer would be used in. And then I'm going to show you the next slide. You don't have to write anything on it because it's a circuit diagram. I just want you to try to, like, I want to talk about the circuit diagram, but you don't have to write this down. Okay, so this is the logic that's inside the multiplexer. So A and B are your switches. And then these are just your inputs, right? This is like your phone on Bluetooth or whatever. This one's your TV, this one's your home stereo. I don't know what you have, right? Just different inputs. So what happens is, so when it's, so say the switches are both set to 0, 0. 0, 0 says that it's supposed to let the output be input 0 should be going to the output. So if we have 0, 0, so A and B are both zeros. So hang on, let me switch colors for the zeros. So A and B are both zeros, right? So this goes through the inverter. It's now a 1 on this wire and a 1 on that wire, right? But look at the D0. So we got this source coming in here. This is only going to let these through if all 3 are 1s. So follow this back. This one's always going to be a 1 because it's as long as it's on, right? So if this is on and the switches are at 0 and 0, because look what happens. This is a 1 now, and we'll follow that up. So now we've got a 1 coming in there. This is a 1. Follow this up. It puts a 1 right there. And if this component is on, now this AND gate will let it through. And if there's anything, now let's see what's happening with the other ones though. Right here, this could be potentially all of these could be 1s, right? You could have all these equipment on. Let's say the situation is all of your different input equipment are on. So is D1 going to come through? Because right now D0 is coming through. So what will happen to the other 3 should have at least 1 0 at an input so that the AND gate doesn't let anything through, right? Because this AND gate, all 3 have to be 1s in order for the current to go through. So follow this. This one right here, let me change colors. So this just connects to D1, so that's a 1. This connects to the same line that you're on here, that's a 1. This bottom one goes down here, that's a 0. So this one doesn't let anybody through. Then we've got a 1 coming from D2 into this AND gate, but then we've got a 0 right here. So that was a 1, that was a 0. So as soon as there's a 0, we know that's not letting anybody through. And where is this bottom one going to get a 0 from? It actually has 2 zeros. These are both going to be zeros. If you follow this one, it comes over to be a 0 at B. If you follow this one, it's over here a 0 at A. So when the switches are set at 0, 0, this is the only gate that lets anything through. So it's letting through that signal that from this source. And then this OR gate just says, oh, is there anything there? Now these are all zeros, and that's a 1. So it's just going to let that 1 through. So we could go through similarly for the other 0 and 1 configurations, but that would take a lot of time. But you can see how like the logic gates kind of determine which input will be let through. This is what the different multiplexers would look like in multisim. You've got your single output over here, and they often put an inverted output, just depending on the application, you'll just use one or the other. Here's your 4 inputs, and then you've got your selector lines. And this enable here is just kind of, I think that just brings like power to it's kind of like having power. You would run power to that, or since this has an inverter, you'd probably run a digital constant of 0 or something. But we'll talk about how to wire them at a later date, if we're ever allowed to wire them. Okay, so now a demultiplexer is basically like the reverse of a multiplexer. There's you have multiple output destinations, but only one input, one source. And then same thing with select lines. Those are still going to be switches. So can anybody think of an application where a demultiplexer would come in handy? If you have one source but different destinations. So what's going to happen here is you've got one input, and the demultiplexer, based on your select line switches, will determine which output receives the input. Right? Only one of these output destinations is going to receive the signal from our source. A charging outlet. So you would have one source, which would be like the power supply, and then if it say it was like a charger that had different charging ports, and then based on but it would have to be a situation where like only one port is allowed to charge at a time, and then the switches would determine which of the ports received the power supply. The next slide has a pretty good like a visual or like a real life scenario where a demultiplexer would be beneficial. Okay, so let's look at what that would be. So in this situation, your single source could be your like computer. Nice 80s computer there. So it's putting out a signal, right? But where do you want that signal to go? Do you want it to go to the printer, the fax machine, this other color printer, a pen plotter? So it's got like it wants to print, but there's several different printers, and the switches will tell it which of those printers to send the signal to. And then it's going to have similar sort of logic, right? You've got one input, then it's going to be connected as an input on each of these 3 input AND gates. And then based on the switch values, it'll determine which it goes to. Okay, and this is what they would look like in multi-sim. And then here's where it kind of like comes and meets with real life. So you've seen like digital displays, LCD, things like that. And it seems like say you're looking at the scoreboard at a basketball game. It seems like if the score was 75, like the 7 and the 5, those segments are lit the whole time, right? But that's not actually what's really happening. It's kind of like it plays tricks on your eyes. Like your eyes and your brain together can only like process visual input so fast. Like it's kind of like card tricks and stuff where people just move so quick, they can do it so fast that it looks like it just disappears. That's because like your eyes can only perceive at a certain frequency, like frames per second. And if something is flashing at a faster frequency, it'll look to us like it's constantly on. But what's really happening is that if you think about like a big display, this would have to have like a bunch of different LEDs lit up at the same time if we were doing it all at once, right? And that lighting up a bunch of different LEDs would take a lot of current. It will take more current. But the thing about computers and electricity is it goes super fast. So what we can do is we can actually just light up one segment at a time, but cycle through them super fast, so that basically what's really happening is you have like a bit of current just running through all these different places and lighting them up real fast, but it happens so fast that it just looks like they're all on at the same time. But in actuality, you're only lighting one at a time, so it takes a lot less current. The more like LEDs that get involved, you could have like a serious power drain on your hands if we didn't cycle through like that. And so a demultiplexer would be able to say, all right, there's all these different, like each LED would be a different output or a different destination. And then the multiplexer, I mean, you would kind of think about, somebody would have to be hitting these switches super, super fast, right? And since humans can't do that, we've come up with a way for the electronics to do it. So this circuit would be these letters would be lit up the entire time, right? And so, I want to show you this real quick. So like for this circuit, this is very similar to that circuit that we just showed, right? Right here, it takes 21 segments to display the word open. So it takes about, to light each segment is about 90 milliwatts of power. To display the word open, 90 times 21 segments, 1.89 watts of power is required. This may not seem like a lot, but think about all the displays you see every day, and each little thing is an LED, right? This is only 21 of them, and we're already getting up to almost 2 watts. So if all of the LEDs that we saw were always lit, we would use so much more power. But we cycle through, and it tricks our eyes and uses like a fraction of the power. Okay. So for this one, it would have to be running power to 18 segments at once, right? So a way to use less power, here's a demultiplexer. And then, so this is, like, remember we said the select lines were basically switches? So this is like if we had actual manual switches. And what happens is as you switch these switches, you go from 0, 0, 0, 1, 1, 0, 1, 1, and you keep cycling through. At 0, 0, C will light up. At 0, 1, the I will light up. At 1, 0, this one will light up, and at 1, 1, this one will light up. But people can't flip switches that fast. Like our hands usually aren't faster than our eyes. So this is like not a practical way to do that, right? With manual switches. But what we can do is create this thing called a ripple counter. And basically what this does is this is called a clock timer. And this is like one of the power sources we can choose in multisim. And what it does is it just sends a little clock timer signal. And the frequency here is 1 kilohertz. That means 1,000 of those per second. So it just sends out a little thing 1,000 times. It sends out a signal 1,000 times per second. And what that does is every time it sends a signal, like this is like a 2-digit binary counter right here. And what happens is every time this guy gets a signal, it flips this from a 0 to 1, and then whenever this one changes, it makes this one flip back and forth from 0 to 1, and then this one is designed to flip back and forth whenever that one does, or the other way around. I think this would be the least significant digit here, and that would be the most significant digit, because the clock timer flips this one back and forth every time, and this one is designed to flip back and forth every time that one goes from a 1 back to a 0. So this little setup right here, what it does is it counts binary super fast, because this is clicking 1,000 times per second. So that means that they count through a 0, 1, 2, 3, 0, 1, 2, 3, like 250 times a second. So that cycle will happen. It'll flash the word chow 250 times a second, right? And that's fast enough for our eyes to perceive that it's always on, that all of them are always on. And in the next unit, we're going to learn how to design these counters. And there we go. That's the end. We made it.